Okay, diving right
Yeah.
into it, we're tackling something pretty fundamental today,
Mm.
refraction.
Yeah.
It's like we see it everywhere, right?
Yeah.
Like that bent straw in a glass of water
Right.
or those dazzling rainbows after a storm.
Exactly.
We kind of think we've got a handle on it, but there's a whole lot more to this story.
Absolutely. Yeah. It's way more than just that simple explanation. Oh, light slows down in a medium. To really get it, we got to go deeper.
And lucky for us, we've got like the ultimate guide for this kind of adventure.
Right. Richard Feynman.
Feynman.
Oh,
Yeah,
yeah.
you got the Feynman lectures, right?
Exactly.
Legendary stuff.
Absolutely.
So we're cracking open chapter 31 today, right?
Yeah. Chapter 31, the origin of the refractive index.
The origin story, I like it.
Yeah. And Feynman, he had this way, this real knack for taking the most brain-bending ideas and making them, like, crystal clear.
Oh, yeah.
And that's our mission today.
Count me in. So where do we even begin with this whole refractive index mysteries? Like, what's the starting point?
Well, Feynman, meticulous teacher that he was,
Yeah.
always got to start with the fundamentals.
Yeah.
So he reminds us of two really key principles.
Okay.
First one, the total electric field, right, at any point.
Hmm.
It's the sum of all the individual electric fields from every single charge around.
So it's like every charge is in on this, like a giant electric tug of war kind of thing.
Exactly. Yeah, it's like this big electric party and every charge has an invitation.
I like that.
Yeah, they all contribute to like the overall vibe, the electric environment.
Okay.
And this leads to like the second big point. The field from each of those charges, it always travels at the speed of light.
Okay.
Even inside a material, like even inside a piece of glass, for example.
So that's interesting because you would think if light slows down in something like glass, then the fields from charges in that glass, those would be slower too, right?
Right, you'd think so, but that's not how it rolls.
So then how does it work? Like if the fields from the charges are always zipping along at the speed of light, why does it look like light slows down when it's in, say, a glass of water?
Yeah, it's a great question. And this is where Feynman sets up this scenario, to illustrate it. Picture this. A thin glass plate.
Okay, got it.
And we've got light shining on it.
Mm-hmm.
What Feynman wants us to really focus on is how the electric field of the light
Yeah.
interacts with the electrons within the atoms of the glass itself.
Okay, that makes sense because light waves, they have electric fields.
Absolutely.
Well, everything's made of atoms with electrons, so yeah, there's got to be some kind of interaction happening there.
Exactly. Now, you know how I said Feynman was all about clear explanations?
Mm-hmm.
Well, he models those electrons in the atoms as, get this, tiny oscillators.
Tiny oscillators.
Yeah, kind of like imagine tiny little springs that can be like stretched and compressed.
Oh, like those springy doorstops you see sometimes.
Yeah,
They have that natural rhythm when you bump them and they go back and forth.
perfect analogy.
Yeah.
So just like a spring has its natural frequency, right? That frequency at which it likes to vibrate.
Yep.
These electrons, they've got their own natural frequencies too.
Okay.
And when the light's electric field comes along, it's like it's driving those tiny electron springs, pushing and pulling on them, making them oscillate.
So it's like this whole dance is happening at the atomic level.
Exactly.
I love it. Electrons doing the wave.
Yeah, but the question is, how does all of this explain why light seems to, slow down in the glass?
Right. That's the million-dollar question.
Yeah, and that's where it gets really wild. Those oscillating electrons, right, they get all energized by the light's field.
Okay, yeah.
And they start acting like, get this, tiny antennas.
No way. So now they're sending out their own signal.
Yeah, they start emitting their own electromagnetic waves.
What?
Now, hold on. These waves, they're not exactly light as we see it, but they still mess with the original light wave that's trying to pass through.
So it's like interference, kind of like when you throw two stones in a pond.
Yeah.
And those ripples, they either clash and get bigger or they sort of cancel each other out.
Exactly. That's a perfect analogy.
Okay.
And this interference, this is key to understanding this whole refractive index thing.
Yeah.
So, see, the interaction between the original light wave and the waves coming from those busy little electron antennas causes a phase shift.
Phase shift. So that's like the delay we're talking about. It's like those two runners starting a race in different times.
Exactly.
Got it.
And as we'll see, this phase shift, it's directly related to the refractive index, or N, as we like to call it in the biz.
Okay.
It's not simply that light slows down.
Right. It's more complicated than that.
It's more about this whole intricate dance of charges and fields
I like it.
that's causing a shift in the light wave's rhythm.
It's messing with its groove.
Ex-
Okay, so we've got electrons doing the wave, causing interference and messing with the light's timing. But how does this phase shift actually connect to the refractive index mathematically? Like,
Yeah.
what about the different types of atoms and the frequency of the light itself? We've got to break down those details.
Oh, we will definitely break those down, but for that fascinating dive into the specifics, you'll have to join us for part 2 of this deep dive
Oh, the suspense.
into Feynman's world of refraction.
Don't even think about changing that dial because you won't want to miss this grand reveal. All right, we're back on the case, still trying to crack the code of the refractive index. And with Feynman as our guide, I feel like we're in good hands.
Oh, absolutely. And this is where we really get to see Feynman's brilliance. He takes this whole intricate dance of charges and fields, and he actually translates it into like a clear mathematical relationship,
Okay.
a formula for the refractive index itself.
Ooh, a formula. I have to admit, formulas, they can seem a bit intimidating sometimes, but they're also like secret codes,
They are.
that unlock these deeper truths about how the universe works.
Yeah.
I'm ready to decode.
All right, let's decode. So think of the refractive index, denoted by n, right, as this kind of a recipe
Okay.
for how much light will bend in a particular material.
Okay, so what are the key ingredients in this recipe that determine how much that light's going to bend?
All right, so first up, we've got the density of atoms in that material, represented by n.
Okay.
And that makes sense, right? Like a denser material with more atoms crammed in, that's
Yeah.
going to have a stronger effect on how the light bends.
Yeah, more atoms, more obstacles for the light to get through, right?
Exactly. More atoms, more of those electron oscillators we talked about.
Right, right.
So their properties, those are crucial too.
Okay,
We've got the electron charge, Q sub E, and the electron mass.
okay.
These tell us, like, how strongly the electrons get affected by the light's electric field, right? And how easily they get jostled around.
So it's not just how many electrons there are,
Mm-hmm.
but it's also their individual characteristics
Exactly.
that are factoring in.
It's like, think about, like, if you flick a bowling ball versus if you flick a ping pong ball,
Yeah.
they're going to react very differently, right?
Okay.
So similar idea here with those electrons. And here's where it gets even cooler. We also have to think about the natural frequencies of those electron oscillators,
Okay.
those omega sub naught guys,
Mm-hmm.
and compare them to the frequency of the light itself, omega.
Okay, so why is it important to compare the light's frequency to the electron's natural frequency?
Okay, so imagine like pushing someone on a swing set, all right?
Okay.
If you push them at just the right rhythm, matching their natural swinging frequency, they're going to go higher and higher.
Yeah.
But if you're offbeat, your pushes are random,
Right.
they're not going to swing as smoothly.
It's all about the timing.
Exactly.
Right.
It's all about the timing. And it's the same idea here. When the light's frequency matches up with the electron's natural frequency, you get a bigger effect.
Oh. So that explains dispersion.
Yes.
Like when you have a prism
Exactly.
and it breaks the white light into a rainbow
Yes, that's exactly it.
because the different colors of light, they have different frequencies, right?
Exactly, yes. So
Yeah.
red light, lower frequency,
Okay, yeah.
blue light, higher frequency.
Got it.
And because of these frequency differences, they each interact a little bit differently
Right.
with those electrons in the material, which leads to slightly different refractive indices,
Oh, cool.
and therefore different bending angles.
So that's how we get that cool separation of colors in a rainbow.
Exactly. It's all thanks to those tiny electrons dancing
How
with the tune of light.
But what happens if the light's frequency doesn't match the electron's natural frequency?
Well, that's when we get what's called anomalous dispersion.
Anomalous dispersion. That sounds juicy.
Yeah, it's fascinating stuff.
Yeah.
So originally, it really puzzled scientists because they saw cases where the refractive index actually decreased with increasing frequency,
Yeah.
which seemed totally backwards,
Right. Like it was breaking the rule.
Exactly. Like, wait, what's going on here? But Feynman's model, it actually explains that both normal and anomalous dispersion are perfectly natural.
Okay.
It all comes down to how closely the light's frequency is lining up with those natural frequencies of the electron oscillator.
Oh, so what they thought was an anomaly was really just like a deeper level of understanding this interaction
Exactly.
that they hadn't gotten to yet.
Exactly. They were like, oh, this is weird. And Feynman's like, no, this makes perfect sense. Look.
Feynman's got the inside scoop.
Yeah, he's like, let me explain.
Yeah.
It's all good.
Okay, so Feynman to the rescue once again.
Always. But he doesn't stop there.
Of course not.
He's like, hold my beer.
What else does he do?
He's going to introduce us to something called the complex refractive index.
Complex refractive index. Okay, I feel like we're getting into some advanced physics here.
It's not as scary as it sounds, I promise.
Okay.
Remember how we talked about the imaginary part of a complex number often represents something that's like oscillating or cycling?
Right, like a wave going up and down, up and down.
Exactly. So in this case, the imaginary part of the refractive index, denoted as N double prime,
Okay.
represents the absorption of light by a material.
Whoa, okay, so now we're not just talking about the light bending, but also some of it's actually getting absorbed
Exactly.
by that material.
It's like imagine rolling a ball on a carpet
Okay.
versus rolling a ball on like a smooth, hard floor.
Yeah.
That carpet's going to absorb some of that energy, right? And it's going to slow down faster.
Right.
Same idea here with the light.
Okay.
So how does this absorption play into the refractive index? Well, now, instead of just having one number for the refractive index, we've got two parts. We've got the real part that describes the bending, and we've got the imaginary part that describes the absorption.
So it's like we're getting a more complete picture
Exactly.
of how this light is interacting with the material.
Yeah, it's like we're going from like looking through a single lens to putting on 3D glasses, you know?
Yeah.
We're getting this whole extra dimension.
This is blowing my mind.
It's pretty awesome, right?
Right.
And this idea of absorption, it's not just some theoretical thing.
Yeah.
It explains a lot of real world stuff. Like, have you ever seen those like dark lines in the spectrum of light from the sun?
Oh yeah, it's like someone took a Sharpie and just like drew black lines on a rainbow.
Exactly.
Look what's going on there.
Those are called absorption lines.
Okay.
And they happen because specific frequencies of light are being absorbed by the gases in the sun's atmosphere.
Oh, interesting.
So as that light travels from the sun's core out to us, it's got to pass through those cooler gases.
Right.
And those gases are made of atoms, right? With their own sets of natural frequencies.
Right.
It's kind of like those gases are picky eaters.
Okay.
And they're only absorbing the colors, the frequencies that resonate with their own internal frequencies.
So those dark lines, they're like fingerprints.
They are.
They're telling us what the sun is made out of.
Exactly. And it's not just the sun. Astronomers use this principle to study the composition of stars and gas clouds, you know, all over the universe.
That's so cool.
Yeah.
So by understanding this complex refractive index, we can like decode the very makeup of stars that are like light years away.
I know.
It's amazing.
Feynman's insights, they just open up these incredible doors.
Yeah, they do.
To understanding the universe in a whole new way.
This is amazing. But there's more, right?
There's always more with Feynman.
Of course there is. He doesn't just stop at like dispersion and absorption, does he? What else is there?
So he takes us even further down the rabbit hole.
Okay.
And he starts exploring the energy that's carried by these light waves themselves and how this connects back to our understanding of diffraction.
Whoa. Okay, we've got to take a quick break, but when we come back, we're diving into the energy of light waves and revisiting diffraction. All with Feynman at the helm. Don't go anywhere. And we're back, diving deep into the fascinating world of the refractive index with the one and only Richard Feynman.
You know, it's funny, we've been talking about this refractive index, and you might think, okay, we've covered it. Bending light, absorption, what else is there?
Right. Like, wrap it up already.
But with Feynman, there's always more. It's like he can't resist pulling another rabbit out of his hat.
Okay, so what's the next rabbit? What's he pulling out now?
Energy. The energy carried by a light wave. Feynman is like, oh, by the way, we can figure out the energy of a light wave using this whole refractive index thing.
Okay, you know I'm always up for an energy calculation, so let's do it.
Remember how we were talking about the imaginary part of the complex refractive index? That N double prime that tells us how much light gets absorbed?
Right, like how much energy the material is soaking up.
Exactly. So Feynman takes this idea of absorption and he combines it with this really fundamental principle, the conservation of energy.
Energy conservation, that's like physics 101.
Right.
Like, can't create it, can't destroy it, just transform.
Exactly. Energy can change forms, like light can turn into heat.
Right.
But the total amount of energy in a closed system always stays the same.
Okay, so where does this lead us in terms of like light and refractive index?
So picture our trusty glass plate again.
Okay, back to the glass plate.
Light wave comes in, hits the plate. Some energy goes through, some gets absorbed, right? And we're assuming, for simplicity, that none of it's getting reflected.
Right, because it's a really thin piece of glass, mostly transparent.
Exactly. So Feynman sets up this energy balance sheet.
Yeah.
He's looking at the electric fields before and after the plate, brings in the absorption, that a double prime.
Okay.
And through some really elegant math, he arrives at this super cool result.
Drum roll, please. What's the result?
The energy carried by an electromagnetic wave is directly proportional to the time average of the electric field squared.
Okay, break that down for me a little bit. What does that actually mean?
Imagine the electric field of a light wave. Right. It's like this wave that's constantly going up and down, up and down.
Oscillating.
Exactly. What Feynman found is that the energy carried by that wave, it's directly tied to how big those up and down movements are. But here's the thing. You got to square them.
So stronger waves, more energy.
It's like the bigger the wave, the more punch it packs.
Makes sense.
And this relationship, it's not just some random thing about light. It pops up everywhere in physics. Antennas, lasers, it's all connected.
Wow. So we've gone from a bent straw to unlocking the secrets of the universe.
And you know Feynman isn't done yet. He's like, hold on, there's one more thing. He connects all of this back to diffraction.
All right, diffraction, where light bends around corners and stuff.
Exactly. Remember we talked about how when light hits a screen with a tiny hole, we can think of that hole as if it's emitting light itself.
Right.
Feynman's like, well, my electron oscillator model explains that too.
Of course it does.
Those charges at the edge of the hole, they get all excited by the incoming light and start oscillating.
Right. Like those tiny antennas.
Exactly. And guess what? Those oscillating charges, they send out their own waves.
So it's not just the light going through the hole.
What?
It's the light that's like interacting with the stuff around the hole.
It's like the hole becomes this little light factory.
I love it. Feynman's model, it just keeps explaining things.
It's amazing, isn't it? This whole deep dive has been incredible. We've covered so much ground, from bending straws to the energy of light waves, and it all comes down to these tiny little interactions happening at the atomic level.
It's like we zoomed way, way in and discovered this whole hidden world that explains how everything works.
And the craziest part is we just scratched the surface. There's so much more to explore in the world of physics, but for now, we'll leave you with that thought.
This has been The Deep Dive. Signing off until next time, when we take another deep dive into the mysteries of the universe.